Well, hi everybody and welcome back. So this next project is something that I've wanted to have on my bench for quite some time, and finding a good example of one of these is very difficult. And what we have on the bench right now is a Scott Model 399, and it's a stereo AM/FM receiver. But that's not entirely true. Why do I like this so much? Well, this is a very unique piece of audio gear. You ought to know by now that I don't always look for something that's the holy grail of all sound or the greatest sounding whatever, because it's so subjective. But what really piques my interest in this type of hobby are things that are unique and different and historical, have historical value. A lot of you ask, heck, I can get a digital whatever stereo class D that has 0.0001% distortion at 9,000 watts. I don't really care about any of that. It's a given that you can always find something that has better specs than something else. What it is with these things is the historical value and getting into the minds of the people who designed this, what they were thinking, what challenges they were trying to overcome. And this here is a very good example. These have a story behind them. That's why I've wanted one for a while now. First of all, they're just beautiful. Look at the way this thing's laid out. And just the things like the reduced tuning adjustment, the separate AM and FM tuning. We'll get more into that in a minute, why. The amplifier is very unique in this. Some of the design elements in the amplifier on this is unique and not totally standard that you would see in everything else from this era. So there's a lot of things in this that are really impressive. The use of the little eye tubes, the magic eye tubes for the tuning strength and so forth. Really neat thing. Now, what is something that's really unique about this is when it was built, the era that this thing came out in. These receivers were built between 1960 and 1962. So you only have a 3-year period that these were being produced between 60 and 62. Now, what's significant about that is that FM stereo, the FCC authorized the regular stereo FM in June of 1961. So it was actually after this thing went into production, a year after. And prior to that, they were experimenting with things called binaural radio. And what they did was they would broadcast the left channel, for instance, on FM and the right channel on AM, and you would have to tune both the AM and FM separately to get your left and right stereo. That was the first attempt. That was called binaural audio, that they were trying to get stereo through, through a radio station. They knew the technology already existed for multiplex stereo. They had already been working with it, but it really didn't start hitting the market till after this came out. And that's one of the things that went into the design of this particular stereo. This is not a stereo receiver. In other words, the FM is a mono FM tuner. But what they did was they prepared it for the future that was very shortly going to come out for stereo broadcast, for actual multiplex stereo broadcast. And of course, this would not be complete if we didn't have the other part of this that came out later. So let me introduce that to you as well. So what this is a Scott model, let me show you here, LM35 wideband multiplex adapter. And you see the word kit? When these came out, you could buy these in two forms. You could buy them pre-assembled factory assembled, or you could buy them as a kit. This particular one is a kit, and by the looks of it, it hardly got any use at all. Because really, shortly after all of this kind of stuff came out, they began integrating the multiplex into the receiver itself, so you didn't need a standalone box. But a lot of these, including the Fisher and other manufacturers at the time, actually would have an output in anticipation of the new multiplex stereo that was coming out. And they were intended for these little adapter boxes. So really what this does is this adapts your mono receiver into a stereo receiver. Some of them, it was very easy to interface this in if they were built the right way. Other models out there really weren't. So for instance, that Fisher 500 that we did, remember we did 2 of those? Those can actually work with these as well. They had a multiplex output that you could drive one of these, but it wasn't very easy to get a stereo sound out of those. You had to have a separate amplifier, a second amplifier for the second channel, and all kinds of things, so you had a lot of challenges. This is much easier the way this works. So this is going to be a 2-for-1 video. We're first going to go through and do this whole receiver as a project. Then we're going to finish up by doing this multiplex adapter as a second project and combine the two in the end and try to receive an FM stereo multiplex signal using this setup and just see how well it works. Because really, how is this going to perform compared to a modern stereo? What kind of stereo separation can we get? What kind of a wide sound can we get? How clear can this receive? Let's see how good they got it, knowing that this was made in anticipation of what was coming out. So if that sounds interesting to you, that's what this series is going to be all about. Okay, as with most of these really cool projects, a collector friend of mine found this, and he is a very thorough person when he does this, when he researches these things, and we were fortunate enough to even be able to find the original photo facts for these. So we have the actual for the FM multiplex adapter, and we have the photo facts for the 399. And if we open this up and we look at some things on the schematics. Okay, looking at the schematic, one of the most impressive things about the design of this is, and I'm sure this circuit is used other places. This is not just Scott. This is, but is the use of this paraphase circuit. It's technically what this is called is a floating paraphase. And when you look at this, originally this type of circuit is not that uncommon in that normally you would see something like a 12AX7 or something like that up here in the front. But this is a special tube called an ECF80, which is a dual pentode and triode tube. And the neat thing about it is in a standard paraphase, you would see 2 triodes. This first triode would drive this side of the push-pull pair, and then this triode would drive the other one, and this one derives its grid drive from this split off here from this first one. But what they've done here is they put a pentode on this side, which provides more gain, so you can get a real high voltage swing. And then they put an AC balance control in here that allows you to adjust this second one to the first one up here. So these 2 channels here, the push and pull side, the positive going and negative going, can actually be perfectly balanced. So even if you have an unmatched pair of tubes, you can actually use this adjustment to compensate for an unmatched pair of tubes, which is really cool. And by having this pentode, definitely one of the downsides is you can introduce noise because of the high gain of this pentode, but you also get a higher voltage swing. so you have more drive and you do it in with less circuitry. So it's kind of neat the way they do this. So anyway, this will be fun to go through and test and do the alignment and everything. It's kind of a unique alignment that they do to have you adjust this, and we'll go over that when we get to that point. But I just thought that'd be something interesting to look at. By the way, you guys ask a lot of questions about the turntable that I use. It's literally a piece of plywood that I just cut and I rounded off the corners. And then this, you can buy these at hardware stores. It's called a Lazy Susan is what we call them over here in the States. I'm not sure what else they call them. This one's, yeah, see, it even says Lazy Susan bearing. See that? And you can buy these very inexpensively at a hardware store. Over here in the States, Home Depot and Lowe's both sell them, and many other places. And you see these in kitchens used a lot, for different types of stands and things, to be able to get to the food. But this one here is pretty heavy duty. Some of these can handle quite a bit of weight. I think this one's good for like 50 pounds or 100 pounds or something like that. So it works really well. And you just screw it down to the board and there's your turntable. Very, very smooth, and it is useful to have on the bench sometimes. Other times I don't like it because the thing goes floating around on you while you're trying to work on it and you're chasing everything. But other times it's nice if you're recapping an amplifier and you have to flip between the front and back all the time. It's nice to be able to rotate it on this instead of picking it up 100 times. Anyway, that's what it is. Okay, we have this up on the turntable so we can kind of see it from different angles. And the first thing I'm going to go over is, even though this, we talked about the tuner on this, that portion, they did not compromise on the amplifier section. It is every bit as unique and fascinating as the tuner on this. There's quite a few vacuum tubes in this thing. And the driver tubes in the front end of this amplifier are very unique. We're going to get into that later. And the output tubes are unique. At first, when you look at these look like your common EL84/6BQ5s, but they really aren't. They're actually a different tube. These are actually 7189s. I don't know if it's listed. Yeah, 7189A. Now, a 7189 is essentially the same as a 6BQ5 or an EL84, but they're a bit higher built. In other words, they have a little bit higher power rating. You can put a higher plate voltage and a little bit higher plate dissipation current, and whereas an EL84, you're going to see EL84 amplifiers or 6BQ5 amplifiers running anywhere from 10 to 15 watts. These ones can run up to 18, and if you really pushed them beyond their limits, you could almost get 20 watts out of them, but I wouldn't recommend it. So if you just plugged in a 6BQ5, quite often you're running those too hot. So you really need those tubes. Now there is a modern replacement for these in the Russian, what is it, the 6P14s, I think. Anyway, they make a military ruggedized version of this, and they have the higher plate voltages and so forth as these, and probably could be made to work in place of these. But I wouldn't just put a standard 6BQ5 or EL84 in there. The power supply is unique. It's also similar to the power supply that we saw in the Fisher 500. This was a big thing back then, where the high current power supply for the amplifier and everything, they used a larger rectifier tube, and then they used a small rectifier tube such as a 6X4 or something to power the tuner, and this is a separate isolated power supply from that that's very quiet, and that's to give the tuner better performance characteristics. So again, they really spared no expense in designing this. And for an 18 watt amplifier, look at the size of those output transformers. They're actually very big. And you can see we can adjust the DC balance. We can adjust the AM and FM level. So they put all kinds of adjustments in these. 4, 8, and 16 ohm speaker, which is pretty common. All in all, very interesting design. Well, I can tell that someone's been in this before because the screws definitely didn't match. They had all different kinds, and when I loosened it up, you could see how warped this is. And that could also be from somebody putting this on top of something and pushing it, but definitely the cover's a little bit bent. All right, let's take it off. And in case you thought that the power transformer wasn't very hefty from the top because it looked so thin, there's the other part of it sticking through the bottom. Yeah, that is a huge power transformer. And you can see from some of the tape and things, they had at least replaced a power cord by the looks of it. But the rest of it looks relatively stock. Definitely crowded inside here, isn't it? I see a little orphan up here. Look at that. That's why we don't just turn things on and power them up. We don't know where that came from or what its purpose was or why it is disconnected. But certainly those are things that we're going to look through and try to find why they are the way they are. These capacitors here, these plastic cased ones, they have a tendency to leak really bad, and we're definitely going to replace all of those, and we'll do some testing on them. That is connected, so that's good. So we'll go through it all, and judging by the discoloration of the wafers here, it looks as if this thing's been thoroughly soaked with deoxit, so they are quite embalmed. So I don't think we'll have to spray any more deoxit on these, but we'll check them. And all right, looks like a project, huh guys? Okay, the first thing I want to do before, this thing has never been plugged in, so, and you saw how many capacitors were in this thing, and we certainly don't want a faulty capacitor to cause any problems, and we just want to make sure there's no shorts. Of course, we could put a dim bulb on there, and that, no problem, but I always like to go through and statically check to see if there's at least any really badly leaky capacitors or shorted capacitors. Now, we talked before that you can use something such as an ESR meter, which you've seen this before, the capacitor wizard, to check the ESR, but an ESR meter is not going to tell you if the capacitor is leaky or shorted, and we demonstrated that on previous videos. But something, what I like to use is I like to use these analog meters, and I'll show you why now. This is a new addition to the bench. Of course, you've seen the Simpson 260 that I have, but I was in an old antique store, and I found this triplet model 630, which I have wanted a good one of these for a very long time. And you can still buy these brand new, but they have those goofy probe sockets like that new Simpson that I have, the reverse banana plugs. I hate them. But this is a really classic meter, and this one came with the clear acrylic back on it, and you can see this thing was just in tremendous condition when I got it. I couldn't believe how nice it was, and I only paid $30 for it, which I thought was a really good price for this meter. But one of the things that a good thing that you can use to test this is, number one, when you have this meter on ×1, ×10, or ×1000, when you're in ohms mode, it actually uses a type D cell battery that's 1.5 volts. So if we go over and put our meter on DC, we're going to use this meter to read this meter. So if I set this to ×1, you'll see that at the leads, whoop, if they don't fall off, you can see at the leads here that you have 1.5 volts, which is your battery, you know, your D cell battery. And if I go to times 10, it doesn't change, or times 100. Now remember, this meter has a 30 mega ohm input impedance, so it's a really high impedance, so it's not really loading this meter down at the moment. If I go to the times 100,000, you can see now it's 30 volts roughly, because there is also a 30 volt battery. It's kind of hiding down here behind this D cell battery. And that 30 volt battery is for the high ohms mode, or the times 100,000 mode. Now there's a little more to it than that. So let's turn back to times 1,000, and we're going to move this meter. We're going to pull this out. We're going to go over to milliamps and plug this in. And you can see the meter actually, it pegs the meter because that shunt inside here acts as a short almost. And you can see that there's about 356 microamps, or 0.356 milliamps of current when you're in the times 1000 mode. So that's kind of the current limiting of this meter. So this meter will output 1.5 volts at a maximum of 0.356 milliamp in this mode. Now if we go to times 10, it's now drawing 34 milliamps. That's getting up to a pretty good amount of current. If we go to times 1, it's almost a quarter of an amp, 244 milliamps at that 1.5 volts. So you don't want to really leave this thing on times 1 for very long, because it will wear down your D cell battery. But the point that I'm making is this actually can put a real load across a capacitor. If we go to the times 100,000 mode, you can see it's very, very low. You're only putting about 0.06 milliamps out. That's why, or you're drawing only about 0.06 milliamps. That's what it's limited to. And that's why that 30 volt battery lasts such a long time in here. But it still does put 30 volts across the circuit that you're testing at a very low current. So this is a very useful thing for testing capacitors, because it actually is a current limited power supply. And depending on what you set your meter to, it can be different voltages and current limits. Now the Simpson 360 or Simpson 260, and really all the analog meters like from this type are like that. And that's an advantage to this. These meters here don't really work like that. They're somewhat different. Same thing with the VTVM. They can be a little bit different. Not all of them are, but just depends on the circuit. But anyway, these volt-ohm meters are very useful. So we're going to use that to check these these capacitors for at least very noticeable leakage and perhaps any shorts. So I hope that kind of makes sense. Now one more quick thing that some of you may mention if I don't bring this up. With the leads shorted, those are the currents that these are limited to. But remember, if you put resistance in here, it's putting a resistor in series, your current will go down because the overall resistance will be up. So Ohm's law. Remember, the voltage will never go above 1.5 volts, so something's got to give. When you increase your resistance, you're going to decrease your current. So that's the maximum amount of current that can flow on each of those settings, but not necessarily how much is going to flow. It's all dependent upon what resistance you're applying across these two leads. Okay, I hope I have everything in shot here. I have the meter set to times 1K, or times 1000, and we're going to read the ohms as this red scale across the top. I hope you can see that. I'm not sure, but I'm trying to get everything in shot. So first thing we want to do is we're just going to check each one of these statically, and you can see this is about 3.5K. And that's probably because there's some circuitry in here. This one is 3.5, so this one is about 4K. That one just jumps and goes right down, so there's no problem there. And if we reverse the leads, you can see it charge the other way. See that? Those are both high resistance on those. On this side, looking at this capacitor, about 4K. That one's good. Good. That's got a little bit of leakage in it. See that? And again, some of this could be that we're reading across some circuitry, and some of that could be leakage in the capacitor. We don't know, but as long as it's not really low resistance, we're okay with that. All right, let's look at some of these down here. That one's good. We're just looking for really low resistance, you know, under a couple thousand ohms. Good, good. Now see, that one's only about 1500 ohms. We'll have to check that one, and so is that one. Of course, this one has a 1.5K across it, so you're reading the resistor. You're not reading any other resistance, so that's this resistor here that we're looking at across the capacitor to ground. So far, so good. All right, let's read this one. Hard to get at these from around the camera. Whoop. There's a dead short there. What's that one? That's not good. Look at that. That's almost a dead short. So that section could be bad. That one's reading okay, not too bad. Dead short right there. And that's almost a dead short. You can see it's just off of the zero. So this capacitor here may be bad. We'll have to look and see if there's something in the circuit causing it to read like that. Going across this cap, it reads bad. So, and these are isolated capacitors. They're not connected directly to ground. Yeah, we're reading all kinds of bad stuff here. So we're going to have to look at this side a little bit more. That might be okay still. We'll have to look in the schematics. Okay, now let's look at the ESR and see what kind of condition these things are in. These are the two tests you should do. That one's good, 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 good. All right, let's go over to this side. That's a little bit tired. That one's good. That one's dead. See that? And that one's tired. So this cap here is bad. Now let's go over to the problematic ones over here and see what they look like from an ESR standpoint. Really bad, huh? That one's dead shorted. See that? That's an actual short. Bad. That one's good. I'm sorry. And that one, from an ESR standpoint, is good. This little cap here, not bad. And let's look at that one's okay. So that guy there's bad, I believe. Not bad. Not bad. That one's tired. Tired. So, and then if we go over to the main, the first one on the rectifier tube, that one's good. And that one's good. So you can see between checking the ESR and the resistance, you can get, at least in circuit, you can get a decent idea of what you're in for when you plug this thing in. And that's kind of what I'm trying to prove. And you can see, if I didn't have a camera in front of me and I just buzzed through it with the ESR meter and buzzed through it with the ohm meter, you can see how fast you can test this. It's really not a big thing. It takes a couple of minutes to do it. And that gives you an idea of what you're going to be applying power to when you plug this thing in and turn it on. Now there is a possibility when we put this on, if we put it in through a dim bulb tester, there is quite the possibility that this could come on very bright, and you could draw a lot of current through, unless you have a small bulb filament, through your rectifier tube. But then eventually, as these warm up, they may reform a little bit and get at least to a usable state. So, but again, once they get like that, I like to replace them. So these are all going to be replaced eventually, but I just want to see this thing work before I tear into anything. Okay, I have the rectifier tubes pulled, and I'm going across the high voltage winding of the transformer, and we're going to just look and see what we get when we turn this on. We're going to check our voltages. So you can see how bright that light is with nothing on. And you can see there's about 115 volts going in there, which is very low. And I wouldn't think, being that we don't have any rectifier tubes in at all, the only thing that's connected right now is that little solid state rectifier, and that's just for your negative bias voltage. So really, with the exception of the filaments of all the other tubes, the output tubes are out and the rectifiers are out, we shouldn't be seeing that much current being drawn, and we shouldn't see that voltage being so terribly low, but it is. So tells me there's some things we probably should be looking at before we apply any kind of power or put the rectifier tubes in. Let's look at the filament winding of the GZ34. That should be 5 volts, I believe, if I can get this thing to connect. Hard to get the lead to stay on there. Okay, here we go. And you can see that's very low. It's not even 1 volt. So that's not good. And let's go over and look at this other winding. Let's see here. Something is definitely shorted in here, isn't it? I'm only getting 30 volts on the 6x4 winding, which is very low. So yeah, all in all, this is very low, and I can put a bigger bulb in there, but I don't see a purpose in that because I don't think we should be seeing this much current draw, and we shouldn't see this much going down. So I don't know. Let me look at this a little closer. Okay, even with that little 40-watt bulb in there, I started smelling something, and then I noticed a little tiny bit of smoke coming out from this area over here. So there's definitely a component shorted somewhere that is either connected to that bias supply or connected to the AC somehow. But there's definitely something shorted in this circuit, and that's why we cannot just go and apply power to this thing. So I'm going to do a little more investigating and find out what it is that's causing this. Another reason you always start off with a dim bulb checker is if you forget to check and see who changed the fuse last. This is supposed to be a 2.5 amp slow blow fuse, or a 2.5 amp. And yeah, they put a 4 amp in there. So I do not have any 2.5s. I will have to get some more, but I do have some 2 amp slow blow, and that will be fine for test purposes because we're not going to run this at high power or anything until we get it working. So I'm going to put that in there just for now, and that should be good enough because we're not going to let this thing off the leash while we're working on it until we know all the power supplies are good and there's no shorts. Okay, as you can see, I have all of the vacuum bulbs pulled out of the chassis now. So there is nothing in circuit, there's no filaments, there's no power supply. The only thing is the transformer itself, power transformer, and the regulated power supply, I'm going to call it, which is that little bridge rectifier right here. And you can see it powers 4 of the tube's filaments for low noise, and it also provides your bias voltage, your negative, what is it, negative 15 volts. So that is the only thing right now that's connected to the transformer. And I did check these, they're okay, they're ceramic capacitors. There's no shorts there. So let's go over here, and what it should do is the bulb should be very dim now because there's really nothing in the circuit to cause this thing to draw current. So let's turn it on. I just plugged it in, so. And as you can see, full brightness. So there is definitely a short either in the transformer itself or in that low voltage rectifier. So let's look at the solid state rectifier first. We'll disconnect that. If the problem doesn't go away, we're running out of options here. All right, I've now just removed the windings from the solid state rectifier in case it is shorted. And let's turn this on. That is not a good sign, guys. That would be absolutely devastating if this transformer was bad. So you can see how many windings are on this thing. So the first thing we need to do is go through each set of windings and check to see if there's any kinds of shorts. Now, these ones here aren't connected to anything else. You could see with the vacuum tube removed, these terminals are empty, so there's nothing there. And we were reading a little bit of voltage across this one, but we were getting no voltage across the 5-volt winding, which means we may have an internal short. So with everything disconnected now, we're going to connect back up to this 5-volt winding, and we're going to see if we get anything there. That might be part of our problem. So let's put this on AC volts. I will put this in front of you here, and let's turn it on and see what we get. Only getting about 1 volt. Now that could be because of the short. The light bulb is taking up all of the voltage right now. It's all dropping across that bulb. So there's a very good possibility that that's why the voltage is so low. There's not a short on that winding. We were reading something. So just trying to look at all this. We were getting readings on these windings. I was reading something. And I was reading something on these windings. And then these two are your center going to ground. So I'm going to have to poke around and see what we can find. I'm now measuring between this winding right here from the ground to there on this filament winding, which is right over here. You can see it. And just a moment ago, we had 6 volts AC with the thing turned off. And now the 6 volts is gone. If I turn it on, I get nothing. There it is, see? Look at that. I have no... The power is not turned on. It's turned off right now. And you can see I'm reading voltage in here. And if I wiggle this connector, you can see it jumps all over the place. Now there shouldn't be any voltage there whatsoever, because if you look, the power switch cuts the power right there. So there's no possible way we could have any voltage getting out to here. And the strange thing is, measuring all of the other windings, see, look at that. If I look at the other windings, I don't get anything. So like here's another winding. There's nothing, which is what you would expect because there's no power. So it's that's really bizarre. Somebody changed the wiring in here, or has a short somewhere. Now you can see where they replaced the power cord. That is not a factory power cord. And you can see kind of how crappy that is in there. Look at that solder job. Not exactly what I would call the best work. I don't know if that has something to do with it, but right over there on our filament windings, we are getting 6 volts. I don't know how it is getting there, and I don't know how it is not getting on the rest of the transformer. And just, you know, if you think it's noise, well, let me back you up. I'm going to show you something here. So I'm going to connect this back on to where it was. Where were we? We were right here. And you can see, wiggling it around, I'm getting, now it's gone again. Look at that. How bizarre. Now it's gone. I have no explanation, gentlemen and ladies. I do not know. And you can see now it's not reading anything. It's like there's no power. Okay, so I removed the 6.3 volt winding. Remember I told you, even with that little bulb on there, I thought I saw a little whiff of smoke there at one time. And it kind of, one of those things, you know, follow the smoke. So we're looking right here at this little winding here, which is your 6.3 volts for the tuner, for all the vacuum tubes on the tuner. So I'm removing one leg of this so that there's no current flowing through that 6.3 volt circuit. Plug the thing in, and let's move this over to here, and let's see if our light comes on now. And how about that? No shorts. So there must be something in that line that's loading this transformer down. Now we're still not out of the woods. We need to measure all of our voltages and make sure they're up to where they need to be. Okay, we still have the lead disconnected here, but we just have our AC voltmeter across there. Let's see what happens. Okay, that's good. 7.2, that's unloaded voltage, so that's what I would expect. Let's check all the other windings now and see if they've come up to where they belong, because I think we're going to be in good shape here. So let's look at the high voltage and see where it is. Okay. How about that? That's more like it. Okay, let's check the filament winding here, which should be our 5 volts, and it's going to be high too, I would think. a little bit high, 5.5. And I'm gonna say all of these are gonna be okay now, which is extraordinarily good news. I was really, really worried there for a little bit that the transformer was going to be bad because there was a short in it. But really, we have a short in that filament circuit somewhere that we're going to have to trace down and figure out. Okay, here's the 6x4 high voltage winding. Very nice. So everything is working like it's supposed to now. All right, as you can see, I removed the filament windings from the transformer from this tube down here, and I separated all of the branches that the filament goes out to. Now that only leaves this little ceramic disc capacitor, and if we measure from there to ground, well, it's kind of hard to see, isn't it, when you don't have the meter in front of you, huh? Let me back this up a little bit so you can see. There we go. Kind of an odd angle, but you can see everything, I guess. If we go from here to here, of course, there's nothing. Now, looking at the schematic, we have these branches here. You can see you have this coil. There's actually two coils that go out because you have point Y and point Z, and you have two of these number 47 bulbs. So if I measure from the two coils, so I go from here to this coil, this goes to a filament of one of the tubes, and this one goes to a filament of another tube, and you can see there's no short. If I go to this gray wire, you see I removed this gray wire down here. I don't know how well you can see it, but it snakes its way all the way around, clear to the other side of the chassis. And if I measure from ground to that, there's your short. Now I'm on times 10 right now, meaning whatever I read, you times it by 10. So I'm getting about, well, it looks like I'm getting about 3 or 4 ohms, which could very well be those two indicator bulbs. We'll have to find those. We could be reading that, but it is not a dead short. So the next thing we need to do is disconnect the bulbs and see if that is what we're reading right now. Maybe there's something shorted on the bulb socket or something like that up front that we're not seeing right now. So we're going to have to go look at that. Okay, I think we're in better shape than we thought. Removing the little shield that was over here to get to the bulbs, first of all, these have been replaced with LEDs, and I checked them and they are good, so there's no problem with the bulbs. But also we had these other 4 vacuum tubes in here. We had the 2 EM84 Magic Eye tubes, and we had these 2 12AX7s up here. And of course those 4 were in the filament string. So what we were reading on the gray wire was the 4 filaments of these 4 tubes here in parallel. So removing those tubes, the short went totally away. So what does that tell us? Does that mean that the short magically fixed itself? No, what it tells me is when I was removing all those clumped up wires on that one tiny pin of that one tiny tube, I believe that there was a short in there between ground and the pin. And the reason being is none of the wires in there had insulation of that one big resistor going across the top. Well, I'll show you here. Okay, you're probably seeing this much better than me because of how zoomed in the camera is and how big the screen is you're looking at or whatever, as long as you're not looking on your phone. But you can see this resistor lead here and this one here, they're going right across. We had a very tight situation where you have the ground lead coming from the center post of this socket. You can see this little lead going down here to ground. Look how close everything was. And there was just a really big ball of solder right on this pin. And I believe it was touching right here. You can just see how tiny the little space is there. So we're going to have to clean up all of this so that that doesn't happen. I really believe that's where the short was, and that's what was causing it to fail. And that little spark that I saw, or at least I thought I saw, I'm sure was coming from right in there. So who knows? Now, I never touched anything over there, so I don't believe I introduced that short. So I kind of believe that that's been like that for a while and probably was intermittently causing problems with this for some time. And that might be also why somebody had replaced the fuse with a 4 amp fuse, because this was probably just barely touching in here for a long time. And it probably was just enough resistance there to blow the 2 amp fuse, and somebody had replaced it with a 4 amp slow blow fuse. So we're going to clean that up, and then hopefully we can apply power. Now remember, we have some bad capacitors in here, so we're still going to not let this thing off the leash. And it's possible that the caps may reform to a point at least that it will work to where we can test this thing. But that remains to be seen after we apply power. And just about as I was ready to pat myself on the back for the wonderful soldering job I did on this terminal to clean it up, yeah, we forgot one. The wheel was turning, but the hamster's dead once again. So let the village idiot go back in and fix this, and we'll be right back. Okay, now that we have the filaments connected back up, and I actually remember to put the wires in, and I put new clampy things on the wires, which is good. Let's plug in. All right, and let's go over here and turn on and see if we get our 6.3 volts. Sure enough, we do. So our filament string is lit. I see light coming out of the indicator lamps, and our dim bulb is dim. Okay, so to make things a little easier, I took the schematic and I just enlarged the power supply section and put it onto a big piece of paper. And because of the lighting here, the way it reflects, you get those dark bands there, but that's just the way it is with this camera. That's a camera thing. And what I'm looking at right now is this section right here to begin with. And I'm just going through and kind of statically checking all the different components in here. I'm just trying to find some clues to get me in the right direction. Now the first thing I found is right here we have your 6x4. It comes off of there and it goes through this switch network. And depending on whether you're selecting the tuner or auxiliary or whatever, it'll switch that voltage, that 190 volts, over to this little network here, which is your little power supply network. You can see where it comes in and goes out. And there is, if you notice, all three of these resistors are called R182. Notice they're A, B, and C. And they're all 250 ohms each. Following through here, here's your 6x4 socket. And there is this shielded cable right here. You see it? It goes all the way around, and it snakes its way all the way over to right here on this selector switch. I don't even know if you can see it down in here. It then comes out through this red wire right here and goes into this, which is your can dome resistor. See it? So from here to here should be 250 ohms, from here to here should be 250, and from here to here should be 250. And if I go through all three, I should have 750 ohms. So with that in mind, let's put our meter in. So we go to our first one, and we measure here. And first of all, it is not 250 ohms, it is 200 ohms. So it's gone up. If I go over to this one, from here to here, it's open. So this section is bad. And if I go from this one to here, that one's reading 500 ohms. So it's reading very high. So this can dome resistor here is bad. That's pretty common. Can dome resistors like this fail. They fail a lot. And if you look inside here, you see inside of this fish paper, see how it's kind of all corroded in there? So this is going to need to be replaced with an actual resistor network. Okay, we're put together, and I don't know if you could see under here, but turn the camera sideways, there is the 6X4. I have that fitted. None of the other tubes are in. And right there is our capacitor that has the all of the sections for the can dome resistor. And as we know, this section between here and here is bad. So that I would imagine is this one right here. So if you look there, that's what we're going to do right now. We're going to power this up, and we're going to see if we get anything out to here. Now, of course, we're going to have to turn this selector switch to get this to come in. But if we don't see anything, we'll know what that is. But we're going to check and see if we have some sort of voltage. I have this on a really heavy current limit, because if this capacitor is bad, which is probably what I suspect caused the can dome resistor to go open, I don't want to damage the 6X4. I do have spare 6X4s, but I don't want to damage this one. 6X4s are very delicate. They don't take much to cause them to fail. So we're going to be very cautious. So with that in mind, let's look over here. And there's just some phantom voltage on there right now, reading across the capacitor. And I have not tried this. I have not powered this up, so that's just what was on the cap, just sitting there. All right, here we go. That's good. We got a little flash of the bulb and it went really dim. Let's see if this thing warms up. And like I said, there's a possibility that we don't have the selector switch in, in which case we won't see anything here. So let's rotate this. Nope. So we're not getting any voltage out of the tube. It's lit up. Let's go back and look at the output of the tube itself. Okay, I'm right at the tube socket now. Let's turn it on. And as the tube heats up, you can see this thing heats up pretty fast. So we do have DC voltage on the tube itself, but we're not getting anything out to the can dome resistor. So it could be something to do with the switch. We may have a damaged selector switch as well, because once again, or I may not have something selected properly, but we may have a damaged selector switch from a capacitor or something shorting out. So let me look into that a little bit. Okay, just as I feared, I think we have a bad wafer switch up here in the front. I don't know if you could see it. You probably can't. It's way down in there. I don't know if I can move the camera a little bit closer, but if you look down in there and I move this off, if I can work around the camera here, way down inside there on this wafer right here, you can see that white wire right there. That's actually the power coming straight from the 6x4, and we do have power at that place. And then if I wiggle this blue wire, you see the blue wire moving? That goes to another terminal just right next to that one, and that's actually where there's a wiper that actually is supposed to contact those two together, and it's not working. So the wafer switch is damaged. We're going to have to remove this switch. I can see this is going to be another one of those here we go again projects. Okay, I don't know if you can see this, but here's the there's the wiper, and see the contacts? Those contacts right there are actually not even touching this. They're actually moved back. So something here has been bent. You see how on this side they're actually clamped inside the contacts, the little wiper, but over here they're not. So it tells me they got caught at some time and bent, and that's why we're not getting contact. So we're going to have to try to fix that. Well, once again, I don't know if you can see this, but take a look right there. Right there. This wafer was broken and glued together. Somebody repaired it, and they did a bad repair. That's the problem. Whoever the seller was that sold this to the owner did not disclose that or did not know that, but that wafer switch is broken. It's been glued together incorrectly, and the contacts are not properly lined up with the rotor. And I don't know if that's a repairable thing. To be honest, you really can't fix these wafers when they're broken, and it looks like somebody sprayed the heck out of it with deoxit, so glue wouldn't really stick very well to it anyway. I guess I'm going to have to talk with the owner, and I'm going to end the video right here, and when we come back, we'll see what kind of solution we can come up with to fix this. Well, till next time, I wish you all peace, joy, happiness, and good health in your lives, and hopefully we won't have to tell this one to rest in peace. We'll see you soon.